I didn't get an email.
I didn't either. So we're going here,
Yeah.
right? All right. Hi, Stanley, if you're there. So we're going to end up with triangulation again, but this is a little bit different kind of triangulation. We triangulated a polygon, and then used it for various things. But the deal was we were given a set of points, and those points were the vertices of the polygon. So the point set that we were given are the vertices of the polygon. I'm going to kick it a little closer. Kick my tongue in the process. They have a bazillion little kids on campus today for some kind of, I don't think it's a ZAP camp, but it's one of those kid activities, and some of them are just little. But anyhow, we were given a set of points that were the vertices of the polygon, and then our triangulation triangulated from that. So the net effect was we added diagonals so that we created so that at least one part of the triangulation actually touched the exterior or touched the edge of the polygon. And so what we were doing is we were partitioning the interior of the polygon. We got, I don't know, the big deal out of this is that for n vertices, we get n minus 2 triangles out of the deal. We're going to look at triangulation a little bit differently. What we'll look at now is suppose the point set aren't necessarily the vertices of the polygon, so aren't necessarily vertices of the polygon. And the goal is to still triangulate, but what are we going to triangulate? I guess let me put a collection of points up here. Nothing magic about this set except that they happen to be what I have in my notes. And then if we go and triangulate that set, so here's a triangulation of it. It's not a very interesting one, but it's a triangulation nevertheless. So here's a triangulation. There are a bunch of different ones. You can draw, a whole herd of them on this point set. But there's a couple of things that happen in this. In the process of triangulating them, I wind up making a polygon. I mean, this particular point set, everybody except this guy wound up on the outside of this triangulation. If I had more inside points, no, let me just add one. Here's another point. Here's another triangulation. So the deal is some of the points wind up on the hull of the resulting geometric figure, and some of them wind up inside. But all of the points participate triangles, and the entire space, the entire plane, if you like, except for the exterior, is partitioned into triangles. So there's an easy way to sort of, I don't know, wrap your head around the idea of what we're doing here. We have the triangulation I guess, first of all, notice that when I do the triangulation, all of these that are on the outside are the vertices of the convex hull. And you can try to rig your point set any way that you want, but in the result, I mean, by that I mean, suppose instead of having this point actually be out here on the edge, I stick him inside. And when I go and triangulate, I'm still going to wind up doing that. So I wind up with a convex hull. So the triangulation really sort of partitions this whole enclosed area. That whole enclosed area is the convex hull. The points around the edge are the vertices of the convex hull. So we're actually partitioning the convex hull into triangles, into non-overlapping triangles. And okay, yeah, I need to ask that the vertices of the triangles are points in the set. Just in terms of complexity, the convex hull comes into play in this. Let H be the number of vertices of the convex hull. So that's, these guys that wound up on the outside. Then the complexity of a triangulation looks like this. We have 2n minus h minus 2 triangles in any triangulation, and 3n minus h minus 6 edges. So any triangulation. You can kind of, so if I took that point set and just drew my triangles differently, I could come up with, a whole nother triangulation, but it would obey these factoids. In fact, it turns out there's exponentially many different ways that you can triangulate a point set, exponentially in n. So there's a lot of them, and it turns out some are good and some are less good. We'll look just a little bit at that near the end here. But thinking about, all right, so the enemy gives me a point set. How am I going to triangulate it? And well, there's an immediate, I don't know if it's brute force. I guess it's probably brute force. Yeah, it would be, because it does try all possibilities. But the enemy gives me a point set. I want to triangulate it. And it's this non-overlapping triangles, vertices of which are the points of the set, that sort of lead to an easy approach. I mean, the basic idea would be repeat until done, and you pick two sites or whatever you want to call them. I guess we were calling them sites when you're doing Moroni, so that's reasonable. Pick two sites. Let's say A and B. So two of the points in the point set. If A, B, that segment doesn't intersect any edge that we've got so far, then we add AB to the edge set. So, we start out with an empty edge set, build it up pair by pair, like that. So thinking about pick two points, A and B. That's a pair of for loops, right? That's a nested for loop setup. What about the intersection? Well, I'd have to keep a list of, so suppose that L is a list of edges. That's what we got to check against over there. So we'd start L out, initially it'd be empty, and then basically for I equals 0 to n, for j equals 0 to n, j not equal to I. We just check to see if pi, pj doesn't intersect an edge in L, add it in L. And checking L is just simply a matter of iterating through it, right? I mean, it's a list, so we would go through one by one and check to see if pi, pj touches the edge that's in L. So basically, this is we iterate through L. The little factoid that I just had up here that there's 2n minus h minus 2. I'm sorry, 3n minus h minus 6 edges means that the length of L is going to be linear. So, L's size is linear. So I'm looking at, n times n times n, basically.
What is the iteration on J there?
Pardon?
What is the iteration on J? Like, is that J plus, or like?
J equals 0 to
And-
n, j not equal to I.
Oh, okay. Oh, makes sense, makes sense.
So we get an n cubed, pretty easy n cubed algorithm out of the deal. And that feels good, but of course, cube is big, and there's I guess our end result is triangles. So there's linear triangles, and it's taking us cubic to get them, and that's a little bit out of proportion, or at least it seems kind of expensive. So a reasonable question is, can we do better? And in fact, it's easy to knock one of the exponents off. In fact, if you're really careful, you can knock that down to n log n. I'll look a little bit at the process for it. We've already made the observation that the convex hull vertices are involved. So they actually are vertices of the triangles, some of the triangles, and we know that when we make the triangles, we effectively stay inside the convex hull. So we're partitioning the convex hull. So a thought is, suppose we first step find the convex hull, find the vertices for it. I'm going to spell vertices. And so that gives us, the outline of this thing. And it's easy to, now we've got a polygon. So we triangulate the polygon, triangulate the resulting polygon. And of course, this polygon is special, it's convex. So let me add that here, the resulting convex polygon. And the deal with a convex polygon is, any time you connect a point to somebody that's not his immediate neighbor, as you go around that, you're creating a diagonal, I'm sorry, a diameter. So in fact, I can triangulate like this. I can connect this guy to his neighbor, connect him to the next one, and the next one, and so on. Just walk my way around and make triangles out of all of those. So every time you connect it to anybody other than the neighbor, then add in the edge that goes back and make a triangle. So I can triangulate the resulting convex polygon, and I can do that just by walking around this. So that winds up being linear cost. I mean, it doesn't involve anything, because we know we're working with a convex set here. It doesn't involve any of the contortions that we had to do to prune and add and whatnot in order to ensure that we were staying as diameters. So that's totally straightforward. But that doesn't get all the points. So now step 2 is 1 by 1. Add in the remaining points. So, all right, all of the points are going to lie inside this convex hull someplace, and so they're going to, we wind up with sort of 2 cases. One case is, here's a triangle that we've got, and the new point lands inside the triangle. And when that happens, then, all right, how did I draw this? When that happens, I just triangulate the result. So that's pretty straightforward. The other case is, you either land inside the triangle or on the line, on one of the edges. So the other possibility is, here's an edge, and here's the added in point. And of course, if this is an edge, if this was an edge initially, somebody in here is a triangle. Maybe up here, or maybe down below, or maybe both. Let's say the worst case, would be both. And so I plop in the new point, and he lands here. Then just divide up whatever triangles are on the line that point lands in. So I guess to draw my picture as a before and after, like I did up above. Here's the point. This becomes, the new triangular rise. I just split the triangles. So the cost for this, first we have to find a convex hull. That's an n log n activity. This part is linear. And this part over here, well, I have to run through and insert, and basically what I have to do is determine which of these cases I have and then add the appropriate lines and then repeat the process. So, this could be squared, could be quadratic. If you're careful about the way that you have taken that representation and now are updating it, you can actually get this down to an n log n. So let me say one or the other. So the end result is if we're just naively approaching this, we get an n squared algorithm. If we're very careful about it and use the appropriate data structure to support this, we can get an n log n algorithm for triangulating a set of points. That's way better than the cubic L group. Instead of a buzz, I'm getting just a killer headache now. I think I take the buzz. Which is weird. The smart, you know, everything's going different today. Is it Friday the 13th? It's not. No, it's the 17th. So this morning I got up and my razor, I can't use a blade because I lacerated myself. But I got up and was shaving, and I figured yesterday the battery on that sucker is getting a little dead. I'm probably going to have to charge it. And so when I turned it on, I sort of expected it to just be kind of flat, and it wasn't. But the moment I touched my skin with it, it went dead. Usually when the battery's dying, it gets slower and slower and slower and slower until finally that little thing that goes back and forth is just going back and forth. But this morning, it had good speed until I touched my skin with it. So I'm thinking there's two batteries in there and one of the cells is tanking. So that's unusual. And so today, instead of getting a buzz, I'm getting a headache. And that's kind of unusual. So in the project where we calculated the area of Nicollet County, which I thought was an interesting application, but maybe not. But there's interesting things that happened in it. When we triangulated Nicollet County, in the process of doing that, I set up a visualization of it just so I could see what was going on. Some of the triangles wound up being like this, you know, little weenie guys, and some wound up being, you know, nice big wide triangles. And there's a problem with these. Not so much in that particular project, but a lot of in pretty much any situation other than that particular project. The problem here is we got a little tiny angle, little skinny triangle with a very small angle. And we talked right at the beginning, we talked about, you know, the problems with representing things using floating point representation on computers. And, you know, it's very easy to get an angle that's so small that it appears to be zero, even though it's not zero. And consequently, the area of the triangle would be zero. But if you were using it to support any other kind of activity, the fact that that angle appeared to be zero could just destroy everything. So the small angle might look like zero when it's not. Whereas a big fat one like this, there's no question about it. So there's no problem here, or less problem. So in some sense, triangulations that have little skinny triangles are bad. So this is generically bad triangulation. And if we have the possibility to do so, it's good to get bigger, fatter triangles, ones that have larger angles in them. So a good triangulation is larger angles. In fact, you could go through thinking about today's problem, the triangulating a point set. You could go through all the different triangulations and sort of, you know, calculate the minimum angle and you know, use that as a measurement to determine how good or bad a triangulation is. And then the goal would be to pick the triangulation that had the larger angles. There's some things that you can do. Let me just, I've got a not very good example of one of the things that one can do with a bad triangulation. So here's a foregone that, you know, we could triangulate this way. And when I do that, of course, I've got little bitty angles. So, you know, we're sort of bad. I can triangulate the exact same foregone if I can try to do it. It's supposed to look like Nevada. And all I'd have to do is flip the edge. And I get rid of that little bitty angle thing. My angles are generically larger. So one possibility, one thought that one might have is, given a triangulation, I could go through it and look for situations like this. Look for groups of 4 points where I could improve the triangulation by simply flipping the edges around, and that is a reasonable approach. Actually, this is, when having this discussion, something like this is called an illegal edge because it yields little tiny angles, whereas this is a legal edge. And so what you would do is you'd run through, look for illegal edges, and try to flip them. There's some nice theory here that we'll do as a fact. First of all, there's one fact is that there exists a triangulation of a point set with no illegal edges. That's either surprising or not surprising. I think it's sort of not surprising if we think about the fact that we could go through and flip edges and create, take illegal edges and turn them into legal edges. The second thing is, and this is what yields an actual immediate algorithm, not a particularly good one, but an immediate algorithm. A triangle has no illegal edge if the circle through the vertices contains no other point, no other site in the point set. By that I mean, here's a triangle, and you can find the circle that goes through 3 points. Can't draw it, but you can find the circle that goes through 3 points. And this is a good triangle if there's no other, there's no other point out of that point set anywhere inside the circle. So, not just down here, but also out here on the 2 wings. So the first thing, this number 2 right here, there's a definition that arises from this, and that's in fact the triangulation that we care about. One way to define a Delaunay triangulation is exactly like this. Every triangle has the circumcircle for every triangle contains no other site. Another way to think of a Delaunay triangulation is it's one of the good guys. It's a triangulation with no illegal edges. So just thinking about how one might make a triangulation, a Delaunay triangulation. This number 2 actually gives us a way to attack it. I could, to make Delaunay triangulation, I could just do this, pick 3 points, and if the circle through them contains no other point, so the circle through them contains no other point, keep their triangle. So loop this, pick 3 points, check their circle. If their circle is devoid of any of the other points in the point set, it's a keeper triangle. It turns out, you know, the only thing that's missing on this, picking 3 points, that's 3 nested loops. To get, you know, so 3 for loops. For I equals 0 to n, for j equals, you know, 0 to n not equal to I, and for k equals 0 to n not equal to I plus I or j. There's our 3 points. Then we got to run through and check all of the other points to see if they lie inside the circle. So this right here looks like, you know, we loop through all the points. So we're looking at, you know, an n cost here, 3 nested loops, that's an n cubed with an n inside them. So we've got an n to the 4th algorithm here. Provided we can figure out how to test insideness without working too hard. And you know, there's a nice linear algebra approach for that. Not quite as nice as the left or right business. So the question is here, how do we check? Basically, how do we build the function that checks to see if a point lies inside the circle described by 3 other points? So how did I define this? I called them, oh God, I called them P1, P2, P3, and let me just call the remaining guy Q. So we want to determine, is Q inside the circle through P1, P2, and P3.
On the circle will count as.
Pardon?
On the circle will count as inside it. Or
Yes.
Okay.
So there are 2 determinants that you can calculate. The first is reasonably ugly. So let's get notation. Let pi be xi, yi, and let q be ab, so that the points look different than the guy that we're testing for. So the first determinant is a 4x4, which means, you know, it's could be a little bit ugly to evaluate, except it's got a column of 1s in it. So it's 1 x1 y1 and then x1 squared plus y1 squared. And then the second column just repeats that, except for the second point. And and then the third point. Oopsie, this is a Y2. And you know what's coming third, the last column, be x, be 1a, b, a squared plus b squared. So you just grind out that determinant. With the column of ones, you know, you would expand on that column, doing the 3x3s that come out of it. And you get whatever you get out of that. And it's really the sign that's going to matter to us. But the problem is with something like this, if I flip the columns or the rows around, all I do is I flip the signs. So we got to have something that also pins down the order that we're considering a P1, P2, and P3 in. So that's a 3x3, and that's just one X1, Y1. That's just our old friend. So we calculate that 3x3. And then the check is, are alpha and beta, do they have the same or different sign? And so A, B, or Q is inside if alpha times beta is less than 0. If they have different signs, basically. It's the only hard part is to figure out. I mean, if you were going to do this with trig or algebra, the only hard part would be to figure out the circle. And then the question of whether Q is inside it or not is trivial after that. This just sort of sucks it all up into a fixed number of arithmetic operations, and then a check at the end. So the big deal is you can do that check to see if something is inside a circle in constant time. It doesn't take any additional effort. So we get a pretty straightforward quartic algorithm, n to the fourth algorithm. But it turns out we can go way the heck better than that. And way the heck easier if we already have a Voronoi algorithm. So I guess the first point here is it's not too hard to do a Delaunay triangulation. It's not quite as efficient as either of the other triangulations, but the cool thing about it is we get, you know, triangles that are not ugly, triangles that have all legal edges in it. But it turns out that the Delaunay triangulation is the dual of the Voronoi diagram. That is, given a set of points, if we form the Voronoi diagram of it, we can just flip over to the dual, and that dual winds up being the Delaunay triangulation, vice versa as well. We could make so if our goal was this, we could make one of these and then flip over to dual to get the triangulation. Conversely, if our goal was Voronoi diagram and we had a Delaunay triangulation, we could just flip over to the dual and bingo, it would be there. So how do you do this? I mean, we've already studied how to make Voronoi diagrams, so presumably we have one of at least two and maybe three approaches to that. So given a Voronoi diagram, now the buzz came. on end sites. So we've got the diagram. Basically what you do is you just connect adjacent, so connect the sites whose regions are adjacent, and the resulting connection diagram, the resulting edges form the Delaunay triangulation. I'll try to draw that. Just here's a simple Voronoi diagram on 3 sites. And so, what do you expect? You connect the corresponding, that's not even interesting, right? We got 3. So let's try to do, I think 5 here is what I've got. The hard part is to draw the dang diagram. So we would have this, this, and then we'll get a bounded one over here. So we'll have this bit because I want to have this here and an edge that's going to come out of these guys. So that would be right there. So the resulting picture looks like, doesn't look anything like that. Okay, I learned.
So given the sites whose regions are adjacent, or connect
the
sites
sites
whose regions are adjacent.
So maybe it's easier to just draw the.
Oh, okay. Draw a line from the site. Got it.
Yeah.
Site to site.
All right. So I think something like this. That looks at least marginally reasonable for a Voronoi diagram. So I would connect. So these guys would be adjacent, and I didn't draw a very good picture here, of course. And these guys would be adjacent. So let me just remove the drawing as I go along here. And these guys are adjacent, so I'm going to put this like this, and then finally these guys are adjacent. So the resulting triangulation winds up like that. So, given a Voronoi diagram, it's a linear process. You just simply run through and connect the cells. So the whole hard work in this, so this is linear, the whole effort here is the n log n construction of the Voronoi diagram. So the resulting algorithm is n log n. And not only that, it's really easy, as long as somebody else does the hard work. That's where I'm going to stop. That's the end of the course, unfortunately. So I will await completed programming projects from everyone. Stanley, you might want to look a little more carefully at the way that you're getting that total area for Nicollet County. Someplace in there, you're, I think, not getting the correct triangles. And what I would do for getting the overall total, and I don't remember if you had done that or not, but what I would do is I would add up the absolute value of all of those determinants and not do any divisions until everything's been added up. And then at that point, do the divide by 2. So I'll see you, Stanley. Have a good rest of the summer down there.